Hi, I'm Guo Cheng Guang, 12 years old, secondary one for NS High School. Well, right now here for this lesson, we're still going on with Theoretical Mechanics Chapter 1, Kinematics. In the last lesson, we had about a ring, and for that ring, we could just take it as a ring, then it goes rotating, or we could just take it as one particle, and it rotates like that. Well, for this time right now here, we are having a disk. So this disk is just like on this 2D surface. Well, this between it is full now. So the disk, we may have different methods to find moment of inertia, but we also want to find kinetic energy, and we finding whether for translation and for rotation whether they can be the same. So for this lesson right now here, this disk, the method I'm going to use will be ring by ring. So you can start from this ring in between, it goes outwards, then for each ring you can find it. So from this part over here, the ring, well, first of all, what do we find? Well, last lesson we had found for one ring. Well, in this part, di. So this just take note that here, well, we can take it as just for one ring. Di from this part. Okay, so what we always use is r squared dn. So that's what we always have used. Alright, so from this part over here, r squared dn. Right now here, this dm, beware, the whole thing, it is an m. So if we just take it for one ring at this part, this actual mass for this part, you calculate it with m over, so you just divide by this whole area. So this whole area, just take note that this biggest radius that we have is capital R. Well, this radius that inside, it may change, is we're using as small r. So this part, but it's only for one part. So to find for one ring of it, we need times. So we can just take it as the perimeter of one circle, or the circumference of one of these parts. But wait, how about the thickness of this ring that we're taking? So the thickness that we're taking will be dr. So that will be what we have in this part. Well, so for this part, we can simplify them. We can simplify them first. For example, pi. So that's what we get here. And wait, there's this dr. So that's what we get first for di. So it's just one ring of the moment of inertia. Then we just integrate on both parts. This part you can just straight away get it, it's an I. Well, let's just see which part of this are constants. So constant 2, well, this m, the mass, it doesn't change. And this capital R, just beware, capital R is this longest radius. And this longest radius, it also doesn't change. So this part over here is a constant. Okay, so we don't need to integrate this part. But what we do need to integrate, we have r cubed dr. So r, this part just keeps changing. Well, it depends on which circle and what is the circumference, or what is the radius. So this is what we are looking at here. So this is r cubed dr. But where does it start? Where does it end? Let's take a look. From the smaller circle, so we can just take it as one point here. One point there, well, the radius that we start with is 0. Then it goes out, and the maximum part that we could have is capital R. So that's for the whole, this is the radius for the whole disk. So therefore, that is the max. So at this part, we integrate, we get 1/4. But let me just write this previous part first. So 1 over 4, then r to the power of 4. So r to the power of 4, well, we just only need to submit this capital R, and this 0 is not used. So it's like this. That means what we'll get is half mr squared. Well, if we compare it with what we had last time, well, the part that you realize is different is this half. So when it is a ring, it is just mr squared. When it becomes a disk, you get half mr squared. Okay, so that's the part that is different. Well, 1.5. Let me just explain this a little bit more with like real life examples. For example, like those bicycles that you ride. With those bicycles that you ride, did you realize the first part they use is a ring? Then they want these parts that connect them to be as thin as possible. Well, how is that so? And why would they want to do that? Like, it's not just directly in a disk. So, according to this part, if you have a disk, well, it can easily stop. So when it easily stops, well, when you ride a bicycle, you don't want it to easily stop. You just want it to keep on going. So that will be why they'll just use very thin bars, so that it is very hard to make it stop, as you have greater moment of inertia. Alright, so that's one part of it. Then the next part that we want to find will be something about this energy, in fact kinetic energy, and for the first part that we're using will be for translation. So this is kinetic energy for translation. So kinetic energy for translation at this part that we will be using. So for the last time, well, we are able to use some of those from last time. Like in the last time, what we had used was half v squared dm. Well, that was what we used for the last lesson, whereas it is a ring. Well, for this part, what we will use, well, first of all, half, we can still use it. V. You want this V right now here. Right now here, it has become a disk. So, we want it to have this kind of thing. Well, for this part, what we will be using was omega r squared. So this is the part that we will be using here. Then dm, you can choose to still write it as a dm first, or you can choose to directly write it as, so first of all is that mass, or you can directly choose to write it as this part. Well, in case if you forgot what does this part mean, or how did you put these two parts together just to get that, let me just explain it over here. So this part is the mass for everything. So divide it by the whole area. So that means this part that you have, or you can just describe it as the mass density. So mass density for an area. Then after that, this is a part, this area that you want to apply it to. So mass density times the area that you want to apply it to, that will give you the mass. And this area over here, first of all, we're just taking it as this circumference of a circle, and this dr here will be the thickness of this, well, you can just say as a ring that you have. Then after that, what we can use is, well, we just simplify them first. So like half to so what we will need to integrate afterwards will be here r squared times r. So you get r cubed. Then after that is dr. So for this part in front, E. So this part, you can't straight away integrate it out. This is what you get. Then for this part behind, you integrate. Well, you can still choose to put this as 0 to capital R, or you can also choose to use, well, the R, you make it become something else. So in all, actually what we will get in all, this is what it comes out to be. But in this way, the answer is correct, but can you understand what does this whole thing mean? No, you cannot. So let's just change this form some more. So what if I just put it as so for this part, we will change it to this form. Well, how can we understand it further by changing it to this form then? Let's take a look. Have we seen something in this form earlier? Oh yes, it is right over here. So we can just change this part into I. So what you will get will be half I omega squared. So this is the part that you will actually get. But let's just think again. What do we get in this part? So if you can think of it, it is actually for rotation at this part. So that means you have made it into this kinetic energy for translation. You have turned it into kinetic energy for rotation. So you have made these two parts equal. So then they have become the same thing. Well, at this point, let me just clarify a little bit more about things. You may be wondering why must we use this omega over here and not using a V? Look at this. This is a disk. This disk over here, if you use V, that means each particle on it, they are having the same speed. But is that possible? Like for example, on the one on the most inside, you can say it as the most inside ring. They only move a little bit. But on the most outside ring, they can move so much in that same amount of time. So that means for each particle, their speed is already different. But omega is about their angular speed. So each of them, in the same time, they only can turn the same angle. So that's why we can only use omega for this part. So in this part, we have shown it for a disk. Well, and the disk, the method that we have been using is ring by ring. Alright. So in this time, I hope that you're clear so far. So I'm just going to end this lesson here. So if you like our videos, don't forget to subscribe to our channel. And thank you for your watching.